Greetings, everyone. Learning as a hobby here. I want to do the summary, sorry, not the summary, the solutions for section 5.4 in Tao's Analysis 1 book. So that's what this video is, my solutions for that exercise set. So let's jump into it. I'll just share my screen. Okay, so starting with the first question, 5.4.1. Tao asks us to prove proposition 5.4.4. Let me just remind you what that theorem says, or proposition. All right, this is proposition 5.4.4, which are basic properties of the positive real numbers. So for every real number x, exactly one of the following three statements is true. A, x is 0, B, x is positive, or C, x is negative, and then a real number x is negative if and only if negative x is positive. And finally, if x and y are positive, then so are x plus y and x times y. So that's the proposition we want to prove. He gives a hint here for the first part. He says if x is not 0 and x is the formal limit of some sequence an, then the sequence cannot be eventually epsilon close to the 0 sequence for every single epsilon greater than 0. So use this to show that the sequence an is eventually either positively bounded away from 0 or negatively bounded away from 0. So that's what I did. So let's prove that first part here. So let x be the limit of an, be a non-zero real number, then an is not eventually epsilon close to 0 for some rational epsilon greater than 0. Then there is capital N, there's a natural number capital N such that the absolute value of an is equal to absolute value of an minus 0, which is greater than or equal to epsilon for all little n greater than or equal to capital N. Then an is greater than epsilon, or an is less than or equal to negative epsilon for all n greater than or equal to capital N. In fact, proposition 4.3.7f implies if an is greater than or equal to epsilon, then an is greater than or equal to epsilon for all n greater than or equal to n. Similarly, if a capital N, sorry, there should be a capital N here. Just so it's clear, a capital N less than equal negative epsilon, then a little n, is less than or equal to negative epsilon for all n greater than or equal to capital N. So let me just remind you of what proposition 4.3.7 part F says. So that's this part here. Let epsilon greater than 0 if y and z are both epsilon close to x, and w is between y and z, then w is also epsilon close to x. All right, so now using that fact, the sequence Bn, where Bn is a capital N, sub capital N plus little n, is a Cauchy sequence that is either positively bounded away from 0 or negatively bounded away from 0. Therefore, if x is not 0, then x is greater than 0 or x is less than 0, and that proves the first part. Right, going on to the second part. Next, let x be a positive real number. Then there's a Cauchy sequence an that is positively bounded away from 0, such that x equals the formal limit of an. Then there is a rational number c that is greater than 0, such that a sub little n greater than or equal c for all little n greater than or equal to 1, then negative a sub n less than or equal to negative c for all n greater than or equal to 1, which implies that the sequence negative an and going from 1 to infinity is a Cauchy sequence that is negatively bounded away from 0. Then that means that limit of negative an is equal to the negative of limit an, which is negative x by definition, and that's a negative real number. And the reverse direction I didn't prove here, but it's done in a similar way. So I just didn't do the other part. But okay, and then finally, let x and y be positive real numbers. Then x equals the formal limit of an, y equals formal limit of bn for some Cauchy sequences, an and bn, that are positively bounded away from 0. Then there's c prime rational that are positive, such that a sub little n greater than or equal to c and b sub little n greater than or equal to c prime for all n little n greater than or equal to 1. Then a sub n plus b sub n greater than or equal to c plus c prime for all n greater than or equal to 1, and a n bn greater than or equal to c times c prime for all n greater than or equal to 1. Then the sequence of an plus bn and the sequence of an times bn are Cauchy sequences that are positively bounded away from 0. Therefore, x plus y equals limit an plus bn and x x times y is equal to limit a and bn are positive real numbers, and that proves the proposition. Okay, next question, 5.4.2. Here Tao asks us to prove the claims in proposition 5.4.7. Let me just remind you of what that proposition says. All right, so proposition 5.4.7 says all the claims in proposition 4.2.9, which held for rationals, continue to hold for real numbers. Unfortunately, I don't think I remember to bring up section 4.2, but you can look back in that section for the theorem 4.2.9. But I listed the names, at least, of the properties that we're trying to prove here. So okay, here's my proof. Let x, y, z be real numbers. Then there's a bunch of parts. So the first part is order trichotomy. By proposition 5.4.4, x minus y is positive, negative, or zero. Then either x is greater than y, x is less than y, or x is equal to y, respectively. And that proves that first part. Part two is order is anti-symmetric. So let y greater than x, then y minus x is a positive number if and only if negative times y minus x equals x minus y is negative. That implies that x is less than y. Part three, order is transitive. Let x less than y and y less than z. Then y minus x and z minus y are positive. Then y minus x plus z minus y equals z minus x is positive. Therefore, x is less than y. Part four, addition preserves order. Let x less than y and z a real number. Then y minus x is positive. Which implies y minus x equals y plus z minus x is positive. That implies that x plus z is less than y plus z. And then finally, part five, positive multiplication preserves order. Excuse me, preserves order. Let x less than y and z be a positive real number. Then y minus x is positive, and z times y minus x is also positive, but that's also zy minus zx. So that implies that this should be x less than y. Sorry, this should have been, sorry, there's just a typo here. It should be less than equal. Sorry, strictly less than. All right, that implies that yz is, and did I write this? Sorry, I wrote this backwards. Sorry, this should be the other way around. Okay, that implies that yz is greater than xz, and that proves the proves the entire proposition. Okay, 5.4.3 exercise 5.4.3 says, show that for every real number x, there is exactly one integer capital N, such that capital N less than equal x less than capital N plus 1. And then he just says here that this integer capital N is called the integer part of x, and sometimes it's denoted by this symbol here. This is sometimes read as the floor of x. We've actually seen that function already in Spivak, so hopefully it's not new to you guys. All right, here's my proof. Let x be the limit of an, be a real number. Then an is a Cauchy sequence of rational numbers. Then for some capital N, a natural number, the absolute value of an minus am can be made less than or equal to 1/4 for all n greater than or equal to capital N. In particular, an minus a sub capital N less than or equal to 1/4 for all n greater than or equal to capital N implies that a sub capital N minus 1/4 is less than or equal to a sub little n less than or equal to a sub capital N plus 1/4 for all n little n greater than or equal to capital N. And by proposition 4.4.1, there are, I didn't bring that section up either. I'm sorry. You could look back in the videos for these propositions. By proposition 4.4.1, there are capital N1, capital N2 in the natural numbers, such that capital N1 less than or equal to a sub capital N minus 1/4 less than capital N1 plus 1, and capital N2 less than or equal to a sub capital N plus 1/4 less than capital N sub 2 plus 1, then either N2 equals N1 or N2 equals N1 plus 1, since the distance between a capital N minus 1/4 and a capital N plus 1/4 is less than 1, right? The distance is a half, so which is less than 1. If x is capital N1 or x is capital N2, then clearly the proposition holds, so we can assume that x is not an integer. Then capital N1 less than a sub capital N minus 1/4. If the first case is, if N1 equals N2, then N1 less than or equal to a sub N less than N1 plus 1 for all N greater than or equal to capital N implies that AN is a Cauchy sequence whose terms are bounded by capital N1 and capital N1 plus 1, which implies that capital N1 less than or equal to X less than capital N1 plus 1 by corollary 5.4.10. That one I can show you because I have section 5.4 up here. Right, this is corollary 5.4.10. Let AN and BN be Cauchy sequences of rationals such that AN greater than or equal to BN for all N greater than or equal to 1. Then limit AN is greater than or equal to limit BN. All right, so that's what I'm using here. And then the second case, if N2 equals N1 plus 1, then X not N2 implies AN is not epsilon close to N2. The constant sequence of the rational numbers N2 for some epsilon greater than 0, then either N1 is less than or equal to a sub little n less than capital N1 plus 1 for all little n greater than or equal to n tilde for some n tilde in the natural numbers, or capital N1 plus 1 less than or equal to a sub little n less than capital N1 plus 2 for all n greater than or equal to capital N tilde for some n capital N tilde in the natural numbers. In either case, the result follows, and that proves the theorem. Okay, next exercise, 5.4.4. Show that for any positive real number x greater than 0, there exists a positive integer capital N such that x is greater than 1 over capital N greater than 0. And here's my proof. Let x be a positive real number, then x inverse is a positive real number by proposition 5.4.8. Let me just remind you of that proposition. That is this one here. So let x be a positive real number, then x inverse is also positive. All right. Also, actually, because we're going to use this in a second also, but the other part of proposition 5.4.8 says if y is another positive number and x is greater than y, then x inverse less than y inverse. Okay, so furthermore, 0 less than 1 over x less than capital N for some capital N and N by exercise 5.4.3. Then proposition 5.4.8 implies that capital N inverse less than capital X inverse, less than X inverse inverse, which implies that 0 less than 1 over capital N less than X. And that proves that statement. Right, next exercise, 5.4.5. Here, Tao asks us to prove proposition 5.4.14, and I'll remind you of what that proposition says. Right, that's this one here. Given any two real numbers, x less than y, we can find a rational number q such that x less than q less than y. Okay, here's my proof. Oh, actually, before I get to my proof, Tao gives a hint. He says, use exercise 5.4.4. You may also need to argue by contradictions. So that's what I did. So let x, y be two real numbers such that x less than y. Then y minus x is greater than 0, which implies that there's a capital N, a strictly positive natural number such that y minus x greater than 1 over capital N greater than 0, which implies that capital Ny minus capital Nx is greater than 1. Assume for the sake of contradiction that there's no integer between capital Ny and capital Nx. Then capital Ny minus capital Nx greater than 1 implies capital Ny greater than capital Nx plus 1, which is greater than, obviously, capital N times x. And by exercise 5.4.3, there's an integer m such that capital M less than equal capital Nx less than capital M plus 1 implies that capital M is less than or equal to capital Nx less than capital Ny less than capital M plus 1. Since there's no integer between capital Nx and capital Ny, and 1 less than the distance between capital Nx, capital Ny, less than the distance between capital M plus 1 equals 1, which is a contradiction, right? One that says 1 is strictly less than 1, which is a contradiction. Therefore, there is some capital M in the natural numbers such that capital NX less than capital M less than capital NY, and that implies that X greater than M over N less than Y, so M over N is a rational number, so that proves that such a thing exists. All right, exercise 5.4.6, let X, Y be real numbers and let epsilon greater than 0 be a positive real. Show that absolute value X minus Y less than epsilon if and only if Y minus epsilon less than X less than Y plus epsilon, and that absolute value X minus Y less than or equal epsilon if and only if Y minus epsilon less than equal X less than equal Y plus epsilon. I didn't prove the second part just because it's very it's almost identical to the one that we, the first part. The only difference is the equals you have to add in there, and so I just skipped it. But anyway, let's do the first part. Let absolute value X minus Y less than epsilon, then by definition of absolute value and the order properties, X minus Y is less than epsilon, and negative X minus Y less than epsilon implies that negative epsilon less than X minus Y less than epsilon implies Y minus epsilon less than X less than Y plus epsilon. If Y minus epsilon less than X less than Y plus epsilon, then negative epsilon less than X minus Y less than epsilon, which implies that negative X minus Y less than epsilon and X minus Y less than epsilon, which implies that absolute value X minus Y less than epsilon. So that shows both directions. That shows forward direction and backwards direction. Because it's if and only if, right? By conditional. And then I just said here, like I said, the second inequality is proven in a similar way, so I just skipped the second part. Okay, next question, 5.4.7. Let X and Y be real numbers. Show that X is less than or equal to Y plus epsilon for all real numbers epsilon greater than 0, if and only if X less than or equal to Y. And we want to show that the absolute value X minus Y less than or equal to epsilon for all real numbers epsilon greater than 0, if and only if X equals Y. So here's my proof. Assume that X less than or equal to Y plus epsilon for all epsilon greater than 0, and that X greater than Y, then, so I'm going to do this by contradiction, then X minus Y greater than 0 implies there is a capital N natural number, positive natural number, such that X minus Y greater than 1 over capital N greater than 0 implies X greater than Y plus 1 over capital N greater than or equal to X, which is a contradiction because that implies that X is strictly less than X. Therefore, that means that X has to be less than or equal to Y. And then second part, if X is less than or equal to Y, then, sorry, this is for the if and only if part. If X is less than or equal to Y, then X less than or equal to X plus epsilon, less than or equal to Y plus epsilon for all epsilon greater than 0 by the order properties of the real numbers. Okay, and now we show the second part of the statement. Let absolute value X minus Y less than or equal to epsilon for all epsilon greater than 0. Then Y minus epsilon less than or equal to X less than or equal to Y plus epsilon for all epsilon greater than 0. Then X less than equal to Y by the proof above implies negative epsilon less than or equal to X minus Y less than or equal to 0, which implies that Y minus X less than or equal to epsilon for all epsilon greater than 0, which implies that Y is less than or equal to X. And if X is less than or equal to Y and Y is less than or equal to X, then that means that X has to equal Y. Lastly, if X is equal to Y, so this is the reverse direction of the biconditional, then 0 is equal to X minus Y for any epsilon greater than 0, which implies that negative epsilon is less than or equal to X minus Y less than or equal to epsilon, which implies that absolute value X minus Y less than or equal to epsilon for any epsilon greater than 0 by exercise 5.4.6. And that's the proof. Okay, just two more questions for this section. 5.4.8 asks us to prove this statement here. Let AN be a Cauchy sequence of rationals and let X be a real number such that, let X be a real number. Show that if A little n less than equal to X for all n greater than or equal to 1, then the limit of AN, the formal limit of AN less than or equal to X, and similarly show that if a little n greater than or equal to X for all n greater than or equal to 1, then the formal limit of AN is greater than or equal to X. He gives a hint here, which I'll read out, proved by contradiction. Use proposition 5.4.14 to find a rational between the limit of AN and the number X, and then use proposition 5.4.9 or corollary 5.4.10. So that's what I did. Right, so here's my proof. Let an less than or equal to x for all n greater than or equal to 1, and assume that the formal limit of an greater than x. So this is, I'm doing this for contradiction. Then there's a rational number q such that the formal limit of an greater than q greater than x by proposition 5.4.14. And since an is a Cauchy sequence, it is not equivalent to the constant Cauchy sequence of where all the terms are just q. There is an epsilon greater than 0 such that the absolute value of an minus q is greater than epsilon for all little n greater than or equal to capital N for some natural number capital N. Then the series of ANs is a Cauchy sequence such that AN is greater than or equal to Q for all n greater than or equal to capital N. Then A sub little n is greater than X for all n greater than or equal to capital N. But this contradicts that A sub n is less than or equal to X for all n greater than or equal to 1. Therefore, the formal limit of an is less than or equal to x. Okay, and then the second part I skipped because it's done in almost exactly the same way, so I didn't prove the second part of the problem, but like I said, it's done similarly, so you can try it yourself. All right, and then this is the last question, 5.4.9. If x and y are real numbers, define the maximum, which we're denoting by max x comma y, of x and y to equal x if x is greater than or equal to y, and y if x is less than y. Sorry, if x is less than y. Similarly, define the minimum, which we're denoting by min x comma y of x and y to equal x if x is less than or equal to y, and it's equal to y if x is greater than y. Right, and then there's a bunch of parts to this. So part 1 asks us to prove if x and y are real numbers, show that max x comma y is equal to negative min negative x comma negative y, and min xy equals negative max negative x comma negative y. So here's my proof. So just using the definition, assume x is greater than or equal to y. That means that x is the maximum of x comma y. Also, x greater than or equal to y implies that negative x is less than or equal to negative y, which implies that negative minimum negative x negative y is equal to the negative of negative x, which is equal to x, which is the maximum of x and y. Right? If x is less than y, then negative x greater than negative y, and max xy is equal to y, which is, if you notice, equal to negative negative y, which is equal to the negative of the minimum of negative x comma negative y. And a similar argument shows the other identity as well, but I didn't prove it here because it's done in a similar way. Okay, so that proves the first part. The second part asks us to show x, y, z are real numbers, show that max xy equals max yx, show that max xx is equal to x, and show that max x plus z is, comma y plus z is equal to the maximum of x comma y plus z. And if z is non-negative, show that maximum xz comma yz is equal to z times the maximum of xy. And then he wants us to say what happens to the last claim of z is negative. So here's my proof. So clearly x is greater than or equal to x, which implies that by definition, max x comma x is equal to x. So that proves that part straightforwardly. Okay, next, let x not equal to y. Then if x is equal to max x comma y, that implies that x is greater than or equal to y, which implies that y is less than x, implies that max y comma x is equal to x. Right? If y equals max x comma y, then x less than y implies y greater than or equal to x, which implies that max yx equals y. So therefore, max xy is equal to max yx. Right. Next, let x greater than or equal to y, then max x plus z comma y plus z is equal to x plus z, which is the same thing as max x comma y plus z. And if x is less than z, then max x plus z comma y plus z is y plus z, but notice that's equal to max xy plus z. So that shows the third identity. Okay, and then second to last, let z be a greater than or equal to 0, so non-negative, and x greater than or equal to y. Then max xz comma yz is equal to xz, which is z times the maximum of x and y. And if we assume the other direction, if x less than y, then max xz yz is yz, which is the same thing as z times y, which is, z times the maximum of xy in that case. Therefore, the third identity holds, right? And then lastly, if z is negative, then x greater than or equal to y implies that xz is less than or equal to yz, which implies that maximum xz comma yz is yz, which is z times the minimum of xy. And same thing, if x is less than y, that implies that the maximum of xz comma yz is xz, which is z times the minimum of xy. So if z is negative, then the maximum of xz is equal to z times the minimum of xy. Right. The third and fourth part are relatively straightforward, so I didn't really do too much with them, but I'll read them out. So part 3 says, show that all the claims in 2 also hold for maximum. Sorry, if maximum is replaced with minimum. I skipped it because it's so similar to the previous part that I didn't feel like wasting my time. But it's done in a similar way if you want to do it. And then the last part here, part 4 says, if x, y are positive real numbers, show that max xy inverse is equal to the minimum x inverse y inverse, and minimum x y inverse is equal to maximum x inverse y inverse. And again, I didn't really show all the work. This follows directly from proposition 5.4.8. I'll just remind you of what that proposition says. That's this one here. So the set by the second part, if y is another positive number and x is greater than y, then x inverse is less than y inverse. So the part 4 here follows directly from that. So I didn't really write it out, but you can do it if you want to be complete. Okay, so I'll stop the screen share here. So that's the end of section 5.4. We still have 5.5 to do and 5.6. So 4 more videos for chapter 5, and then we can get back to Spivak. But remember, when we get back to Spivak, the first thing we're going to do is prove again construct the real numbers, but this time using Dedekind cuts. So we're going to do all of this over again, but using a different method in Spivak. And then once we do that, we'll get back to the differentiation and integration chapter in Spivak. Okay, so again, I'll see you guys in the next video. Give me a like, a subscribe if you enjoy this content. Let me know what you think down below, and I'll see you guys in the next video.